important point. The conceptual site model, it's not really a final product, it's more of a process. So we like to advocate that you're never really done building your CSM. You can always learn more about your site. The idea being that obviously you have to have a starting point. So that was a big focus of the part one of the workshop, was how to build kind of the initial CSM. But as you move through phases of a project, up to and especially including remediation, you can still be building your conceptual site model. Some of the sites that I've worked on, some of the most important sort of components of the CSM were built and really developed during the remediation phase, when, you know, if you're following kind of the linear process, you should be way past that. But if you think about when you're installing some kind of a big remedy, especially if it's like an in situ remedy where you're putting in a lot of injection wells or injection points, or it's a thermal system where you're putting in a lot of borings, kind of high density of borings in a small area, that's a great opportunity to learn a lot about your site. So here's another take on a CSM. This one kind of emphasizes, you know, it's a communication tool. It's written and or illustrative presentation of the conditions at a site. So I've included some of this just to show, you know, it's not just an ITRC thing. There's lots of different versions of definitions of a CSM out there. And here's another one from some New Jersey DEP guidance that again emphasizes the process, that it's an iterative tool as you're building and developing the conceptual site model. You're always adding to it as you learn more about your site. High level, you can think about a conceptual site, physical site itself, so the stuff that we all show on the, you know, the picture on the last couple of slides. But another important part of it, and again, this was talked about during the part one of the workshop, you have to consider the land use and the history of the property. And so in part one, we had a whole module on how you can go back and research a site and, you know, maybe what's happened. Obviously, lots of resources out there for that. But that can to know what happened in the past at a site when you're trying to build your CSM. And as it turns out, we'll hear a little bit later on, when you're using the ISM protocol, incremental sampling methodology, you also have to know about the history and the land use, because that's an important part of how you formulate that approach. So this is a ITRC's recent fractured rock guidance document that came out last year. It's just another view or take on a CSM. So in that document, we came up with this concept of the puzzle pieces, and you need to kind of fit all the puzzle pieces together to have a complete CSM. So that team's take on it was looking at geology, hydrogeology, chemistry, fate, and transport. Another key part of this, especially at fractured rock sites, but really at any site, is you have to have the input of a team to build a great conceptual site model. Even for simple sites, it can be helpful to have other perspectives. Not that a single person can't be really smart and know a lot of things, but it really is helpful to have a lot of different disciplines involved and people with different expertise, just because they're going to see different things. They're going to focus on different things. Again, especially at a fractured rock site, you definitely can't go about it on your own, but even really at any site, other disciplines can help. So focusing in on where we're at, with the part one versus part two of the workshop. For right now, we're assuming we've already built the initial CSM. So we followed, to the letter of the law, what we learned in part one, and we've built, we have some sort of a CSM. What we're doing now is assessing that conceptual site model and identifying data gaps. Based on those data gaps, we're then going to go out and collect some data. So we're going to go through a process that documents what those data gaps are and identifies data collection objectives. So this is what I'm going to be kind of picking little pieces from this morning, is the integrated site characterization document. This was written for DNAPL sites, but the process is really applicable to any site. So, of course, should look familiar to most people. It's a representation of the triad approach. We do advocate, and the document talks quite a bit about using this approach when you can. So we focus on the planning. We definitely advocate for using the dynamic work strategies, looking at the data that you're generating as they're coming in to decide what to do next. And of course, to do that, you can be using the real-time measurement technologies. So as with ITRC team that I've been on over the past almost 20 years, there's a flowchart. So it's really pretty straightforward and kind of intuitive, but it is helpful to kind of step through it and understand all the components to the process. So I think I skipped over a slide. All right. Sorry, I've got a lag here. You can think of the process in 3 steps: planning, tool selection, and implementation. So in the planning phase, that's the top part of this flow chart. This is where we go through what I just kind of talked about: defining the problem, looking at the data needs, as well as the resolution of data that you might need, and then you develop collection objectives. There's a tool selection part in this ITRC this afternoon, but this is all the good information about what these tools are and how to use them. And then at the end of the day, I'll talk about, once you've gone out and you've executed a characterization program, what do you do with the data, and how do you use that new data to update your CSM? A word about DQOs, data quality objectives. When team, we definitely did not want to create anything that was contrary to the DQO process. Really, if you follow, rigorously follow the DQO process, you're going to be following what we're recommending in the ITRC guidance. This is probably a more rigorous way of documenting certain parts of the process, but it's basically the same steps. So going through this, and we're assuming we already have some sort of a CSM. So when we're entering this flow chart, we're assessing that. We're saying, how good is this CSM? What do we know about it? The uncertainties, and what are the data gaps? Example site. That was a real site from members of the TRC team that wrote this document. And this is like this example because it's not a big mega site that's been around for, decades and decades. It's a dry cleaner site, which is probably more typical of what most of us work on. So this is a groundwater plume that had chlorinated solvents, and this is a summary over to the left of what the characterization had been. So pretty standard. This initial characterization had been done, I believe, in the early to mid 2000s. So there were 5 monitoring wells, kind of a standard approach, 10-foot screens, 18 soil borings with samples every 5 feet. So, it's not like they just took one sample from the entire thickness and used that for the soil data. They actually had some vertically discrete data. One thing that probably is going to stand out, they didn't do any kind of a soil gas evaluation, which, thinking back to that time frame, that wasn't all that uncommon. If you were characterizing a site 15 years ago, that maybe you wouldn't think of that right off the bat. And then there was a remedy that was being implemented kind of in this blue circle. That really wasn't, they didn't really have much of a plan for assessing its performance. And from what they could tell, it really wasn't working. So just at a high level visually, the red symbols are above the applicable standards and green are below. So the circles are soil borings, and then the triangles are the monitoring wells that they had. So just taking a look at the CSM, you notice pretty much this groundwater contour is the dashed line. So that communicates uncertainty. There's no data. We don't know how far this goes. The source area is all dashed line, a couple of borings that went, anywhere into the source area. Like I said, they weren't really evaluating the remedy. And then the big thing is there was no VI assessment. So that's defining the problem. Now we take those into data gaps and we consider. So this is an ITRC, this slide's from ITRC training, and ITRC actually borrowed it from Seth, who's going to be the next speaker. So it's kind of completes the circle, I guess. So he knows what this is. Besides Seth, he can't answer. It could be, I don't know, a Lego, a football stadium. I don't know. Anyone knows what that is? How about that? Now anyone? Hopefully you can tell by now. So I would like to say that this is like a, a fancy logo that represents my first name, but no one buys that. So the point of this exercise is which one of these is the right resolution? Because as we increase resolution, you go from 10 by 10 to 20 by 20, that's a factor of 4. What if the cost goes up linearly? And then thinking about it, from here to here, is this last R, kind of depends on what you're trying to do. Maybe, something like this is okay for whatever your objective is. And that's why it's important to match the resolution to the objective. So I like to think about this. If you're characterizing an area that you're going to do some kind of a treatment, let's say you're doing, it's a shallow site where it's, kind of like the dry cleaner site, where it's not that expensive to put in a lot of injection points. And you're trying to decide where you need to, stop installing injection points. Maybe something like this one or the 20 by 20 is okay, because it doesn't matter a whole lot, if you go an extra 10 feet, outside of where you needed to. On the other hand, let's say you're implementing an in situ thermal remedy where increasing the footprint by even 20% makes costs go up a lot. In that case, having the higher resolution to really define the edge of the treatment zone might be worth it. So that's why, again, you have to match the resolution to the objectives. So at our example site, the data needs are additional groundwater sampling because we don't know the extent of the plume. We need to know what's going on in the source, and we need to evaluate the soil vapor. So a word about data gaps, and this is from the ITRC's, the fractured rock training, because this is where it definitely is important at fractured rock sites, but even at unconsolidated sites as well. This idea of significant data gaps. So when we put this term, we're not just using the sort of the regular accepted definition of significant. This is a definition that actually came from one of the state members' guidance. It basically means if there's information that's missing that limits your ability to formulate the understanding of the site, then it's a significant data gap. So another way to think about this is if you can't conclude with confidence whether a release has occurred. So during part 1 of the Back to Basics training, we actually had an example. So imagine like an L-shaped strip mall. So on one corner of the strip mall is an active dry cleaner that's currently operating. The other corner was a dry cleaner that was there like in the 60s and 70s. In the middle, literally between, kind of halfway between those two parts of the building, there was VOC contamination. They had done some sampling and found, kind of from the surface of the ground down into groundwater, they knew kind of vertically where the VOCs were. But at that first stage, there wasn't enough information to tell which source it was from to connect it back to either one of those sources. So that would kind of be an obvious definition of a significant data gap. So it turned out that they did some more sampling kind of in each direction and found out it was the historical dry cleaner. But the point is, sometimes the scientist mind in some people in our project team comes out, and you always want more data. So you have to have this recognition that you're always going to have things that you wish you knew or you wish you could sample for, but you might not need to, at least to move forward to the next step in the process. So that's kind of this litmus test, I guess I'll say, for whether it's a significant data gap. So once you've established that, you've identified the data gaps you need to address, then we're saying to set specific objectives. So this might seem a little bit over the top, but we're talking about writing and quantifying these specific statements that are going to govern everything we're doing in the field. So if you're doing the DQO process, you're already doing that if you're following those steps rigorously. So some examples here, let's say your overall objective is to determine the lateral and vertical extent of the VOCs. Obviously, that was driven by your data gap that you don't know what the extent is. So if we're working on a fractured rock site, for example, your data collection objective might look something like this. So you're getting specific on what you're going to assess, what parameters you're looking for, as well as where. So back to our dry cleaner, you can imagine coming up with objectives that say, We're going to delineate the extent of the dissolved phase plume. We're also going to look at, attenuation and degradation from those remedies. So to do that, we're going to collect groundwater samples at specific depths. We're going to collect soil borings at specific depths. We're going to keep delineating, stepping out until we get to standards. And then we're going to install wells to monitor the remedy. So just taking that a step further and actually quantifying what they're going to do, again, here's restating those objectives, also including the soil vapor that I mentioned before. In terms of resolution, their approach was to collect continuous cores, because as you'll find out in a little bit, they had a field lab out here, so they could handle a lot of samples when they were doing this. Then the plan was to collect groundwater samples every 4 feet. That was probably derived from the geoprobe type tooling that they were using, and then 2 depths of soil gas sampling. So once you've gone through the first 3 steps, then the next step is to document all this in a work plan. And again, this might seem like it's kind of an afterthought, but it's important to get these things down on paper to document the process you're going to go through. So again, we advocate the real-time tools to the extent that you can. You want to think about how you're going to manage the data before you go out there and collect it, and then how you're going to interpret the data as you start generating it. So a word about data type. You can think of generally 3 types of data. Quantitative, this is a true concentration. So you get a compound specific value that you can quantify and compare to standards. That's, parts per million, micrograms per liter. Semi-quantitative is a tool that provides, it's compound specific and it's a measurement, but it's not a concentration. So maybe think of like a passive soil gas collector or something like that, where you get a measurement of a compound, but it's not the same as a concentration. And then qualitative, this is where you're measuring something, say a PID response or a millivolt response on some part of a membrane interface probe unit. You're getting a quantified response, but it's indirect. It's not a direct correlation to a concentration. We'll hear more about this later, but you also have to think about accuracy and precision. Of course, accuracy is how close you are to the real value. Precision is about consistency. When you're stepping through this process, I think our industry has kind of come around to the idea that when you're in the characterization phase and you're trying to build your CSM, and you can use these real-time tools, profiling technologies, MIP, LIF, whatever, there's more value in generating a whole lot of screening level data than there is in installing monitoring wells and just sampling those. Again, when you're trying to characterize a site, you want to use site characterization tools. Monitoring wells are for monitoring remedies. So obviously this kind of, you want to generate accurate and precise data, certainly at certain times if you're evaluating compliance, whether a plume is moving offsite above standards or whatnot. But in a characterization phase, maybe you're satisfied with a little bit less accurate and precise data because you're generating just this wealth of information. So again, on the work plan, you want to document the flexible process that you're going to use, how you're going to evaluate the data. If you can use a field lab for whatever your contaminant is, if you're going to generate enough samples to make that economically feasible, it's a good idea, because then you can look at the data as they're generated. So this was the plan for the dry cleaner site. The red and green borings were the historical sampling locations, and then the yellow were all the new ones that they had planned for. So the plan was to collect up to 5 soil samples per boring. So again, this is a shallow site. Groundwater is only about 20 feet. And I didn't explicitly say it, but it doesn't go very deep. It was only something like a 15-foot thick zone. And then grab groundwater samples. And then do a soil gas assessment kind of throughout the area, ideally at 2 different points vertically. All right, so stepping away from the integrated site characterization process, I want to talk about ISM for a couple of slides. So we're putting this in here because it can be a useful approach when you're characterizing sites, probably mostly for soil samples, although I learned yesterday you can do this for groundwater samples. One of the later speakers is going to go into this in more detail. But what is it? So it's a structured composite sampling and processing protocol, essentially. Ideally, it reduces data variability. and then it gives you an unbiased estimate of what kind of the mean concentration is in a specific volume. The whole key to using ISM is establishing what these decision units are. The definition is this is the smallest volume of soil for which a decision will be made based on the data. So this is an example of what ISM might look like. Let's say you have this boundary here. This is the decision unit boundary. So this is all within a decision. And then you lay out these different replicates. So X's, O's, and triangles. Maybe you collect them in different orders. But the idea is with each one of these, you're going to process and composite all the X's, all the O's, and then all the triangles and get analytical results. So again, we're going to hear more about this later. There's a whole bunch of statistical theory that goes behind this that I guess you can read about if you're having trouble sleeping. Just kidding, it's not that bad. It's actually pretty interesting. Here's some advantages and limitations. You can have better spatial coverage. One big advantage is you have a much higher sample mass, which can help eliminate some of the variability that you have, that's inherent to soil sampling. You can get fewer non-detects, you can get more consistent data. Obviously, there's some limitations. You're not getting as many replicates depending on how you do this. And then you don't really have resolution within your decision unit. So kind of the old way, going back to this, you would collect all these samples and send every one of them off, to be analyzed. And with ISM, you're not doing that. So if you had a hotspot up here, it's just going to get composited in with everything else. So that's why defining your decision units is really important. So we'll hear more about this later with a real example. But if you're interested, ITRC has put out a guidance document on this. There are archived trainings available on Cluin. So that's true for any ITRC training. If the one you're interested in is not being offered live in the near term, you can go find an archive. So here's a screenshot of what they have for ISM. There's a part 1 and part 2. You can download the PowerPoint and then actually download the audio file and then follow along as they taught the course back then. And then the document itself is located at that webpage. All right, so the bottom part of the flowchart, again, hearing about for most of the rest of today is how you actually go out and use these things. And then at the end, I'll talk about data evaluation and updating the CSM. So to kind of set the stage, at this point, we're assessing the conceptual site model, identifying data gaps, setting these objectives, and then we're going out into the field. All right.
Great.
Thank you.